Okay, let's go over a few announcements while of things that are coming up. I think I've said most of these before, but let me make sure you understand them now. My office hours today are modified because, as you heard me talking to Mr. Hollins, I've got to go as soon as I'm out through with this class over to the Birmingham campus and pick up a vehicle. As long as Mr. Hollins doesn't come back and tell me I don't have one there. Okay, so I won't be in my office from 11:15 until probably somewhere around 12:30, plus or minus 12:30. Okay, then I'll only be there until a little before 1:15, because at 1:15 we've got to leave to go on the field trip, because we have to be there before 2 o'clock. So we've got to leave right at 1:15. So very limited office hours today. Okay, now to make up for that a little bit, when we get back from the field trip, I'm guessing that's going to be around 4-ish or so. Could be plus or minus there too. I'll be in here with my class. A few of them still need to take their last test, and several others their final exam. But when they finish that, and I think that's going to be done by 5 anyway, then I'll probably head back to the office then. So I'll probably have some office hours at the end of the day. I don't usually, because usually we go to 5:45, but today I think they'll be finished early, and it's the last day of class. It's a mini term. All right, tomorrow my office hours I don't think will be modified. I had thought that I might have to leave a little early. It doesn't look like I'm going to have to now, because I found out somewhat the itinerary, and the things that are happening early I can miss. Is the things later that I needed to be there, but that's going to give us plenty of time to get there, I think. Okay, I've got to check with the boss. She makes the final call. Okay, we didn't get to talk about it last night. Okay, now let's hit a couple of other things while we're there. This is, did I ask y'all before, any of you in a first mini-term class? None of you are? Oh, you are. Two of you are. Okay, have you done the student course evaluation for that course? Okay, do them for all your first mini-term classes. Okay, they should be all up there for you to do. So please do those. That's how we get our best feedback. Okay, so that's number 1. Number 2, sometime next week they'll probably ask for us to submit midterm progress reports. Okay? And right now, I've received 1 paper and 2 first tests, okay? That means I can, and all those were very good scores, so I don't have to report anything on you guys, okay? You folks that I don't have a score for, technically, I need to put down that you have an F at midterm. I don't want to put down you have an F at midterm, but I don't think it's very accurate. But please get me either a research paper or that first test in next week, if possible, okay? All right. Now, I think that's all I need for that. All right, let's move to Monday. Monday should be a normal day as far as office hours go. But Tuesday, remember, is not, okay? Nowhere close to being a normal day on Tuesday, especially with Jake here. Okay. No, that has nothing to do with it. Okay. Now, Tuesday, I have a doctor's appointment at 10:40, but I have to be there for labs at 9:40. So basically, the combination of those two wipes out this class completely. Okay, we will not meet next Tuesday at all. Okay, now we talked about when and how to make up that class, and I think what I got from y'all was that probably next Friday would be the best time, the best day, but y'all hadn't decided on a time yet. And I think you indicated you would have that decided by today. When would you like to make up the class next Friday? Not this Friday. I was going to say this Friday, but I didn't know if I'd have to leave early. So next Friday, when do we want to make it up? We could do it as early as 8 o'clock, 8:30, 10 o'clock like it normally meets, up to 10:45 would be about as late as I'd want to try to start, because I'm supposed to be off at 12, but I never am. But unless, of course, somebody has to meet later, I'll go late. I don't care. Anyone give me a time?
If we have to meet, like we have to make it up, then I'll just say as early as possible.
Early as possible.
Yes, 10:30.
Second?
I don't want to be here all day.
Okay.
We'll be here till 11.
Okay. What time do you say start?
I would say 10:30.
10:30? Then that goes to 11:45. Is that too late?
I don't even wake up till 12.
Okay. I heard one, and something as early as possible. Is that early enough?
Nah, not good enough for you.
What time will be done at 10:30?
9? No, 10:15. 9? Okay. So Friday, not this Friday, not tomorrow, but next Friday on this campus, in this room, 9 o'clock. Right? Okay. And we'll go 9 to 10:15. If you can't be here, I'll be recording it, and it'll go up there. But that'll make up the class for Tuesday. Okay? All right. And if you can't be here, or if you're late, it'll be recorded, so you should be able to get it on. Okay. So, I probably won't get back from my appointment. About the earliest I could possibly get back would be about 11:45. So my office hours normally start at 11:15. They won't. Okay, they'll start whenever I get back. That'll be plus or minus from 11:45. Okay. Now, that's all temporary. That's just because of my doctor's appointment. The rest of what I'm going to say now will be for till the end of the term. First mini-term, I've had a physical science class in here from 1:15 until 5:45. However, the second mini-term, I have another physical science class, but that because the automotive students are in that, some automotive students are, they don't get out of their class until 3 o'clock. They have a block class from 1 to 3. And so they can't get over here before 3:15 or approximately that. So my class starts at 3:15. So my office hours from after Tuesday, in fact, even on Tuesday, will go until 3:15. They just won't start at 11:15. But after Tuesday, they'll be 11:15 until 3:15. 4 hours of office hours right after this class. So you should have plenty of time to get to me, see me, and that kind of stuff. Okay, the bad news on that is I go till 7:45 every Tuesday and Thursday night, but that's not of your concern, that's only mine. Okay. Now, was there something else to do with that? I don't recall. Seems like something taken into my head would influence that. I can't remember what it was. Okay, any questions? Not just about my office hours, but about Trish or any other thing. Any questions? Period. Okay. If not, as soon as the light comes on the projector, I should have had it on already, we will get started and hopefully finish 4.8. We've just got a few pages, a few examples to go, so it should take people along pretty well. So no questions? All right. Now, harmonic motion. When you hear that statement, does anything pop into your head? What's the first thing you think of when you hear harmonic motion? Anything? Or your head's not popping this time of morning? Okay. Say again?
Something that's moving.
Okay. Yes. Very good. I was wondering if someone was going to say something musical. I thought that's what you said at first. Harmony, harmonic, yeah. But those are things that repeat. If something moving that repeats, that's harmonic motion, basically. If you think about it, the night and day, harmonic motion. The seasons of the year, harmonic motion. Temperature graphs, pretty much harmonic motion. You know, just like anything in nature, somehow is relevant to something in harmonic motion. It's the periodic nature of the trigonometric functions are useful for describing the motion of a point on an object that either vibrates in a regular pattern, oscillates in a regular pattern, rotates in a regular pattern, moved by wave motion, anything such as that. The tides are regular. The movement of the earth around the sun, harmonic motion, the season. All these things are reflective of things that repeat. Sometimes it's very long cycles, but they repeat. In some senses, weather patterns, follow this warming, there's cooling, there's warming. Fortunately, right now, we're warming really, really quickly, That wasn't nature, that's been influenced by us, But anyway, anything that is moved by wave motion. Throw a rock into a pond, and the waves that produce are harmonic motion, periodic motion. If you watch your fishing bobber, it's usually going by harmonic motion, waiting for it to sink, So, for example, consider a ball that is bobbing up and down on the end of a spring, Now, what the setup here is, here's your spring, You attach a ball to it. That ball has some mass, so it stretches the spring a little bit. Now, if you let it come to rest and just sit there, that's its equilibrium position, Now, let's say you were to do this to the object. Let's say you pull it down 10 centimeters below where it's at rest, When you're doing that, the spring is pulling back on you, right? If you pull a little way, it pulls back a little bit. Further, it pulls back more strongly. So down here, it's pulling back pretty hard. So as soon as you release this, what's it going to do? Move back up. Is it going to move back up and stop here? No. When it gets here, it's going at its maximum speed, so that it keeps on going. Its momentum keeps it going until it compresses the spring up like this, and then the spring pushes back, and it goes back down. Does it stop there then? No, because it's still going up and down, And it will continue that up and down motion. Now, in real life, it won't continue it forever, Because the metal has some friction in it, internal friction, and you might need some air resistance and other things. So after a while, it weakens, and then finally will stop. But at the beginning, it does very similar, very close to simple harmonic motion, up and down, going down to 10 centimeters, up to 10 centimeters, down to 10 centimeters, every time passing the equilibrium position on its way. So, that's one example of simple harmonic motion. Now, suppose that the 10 centimeters is the maximum distance that the ball will move vertically up or down. And guess what? If you pull it down 10 centimeters, there's no way it's going up more than 10 centimeters. It would be defying gravity. It can't do it. And then it will go back down. It won't go down any further than 10 centimeters. Oh, with one exception. Let me go back and make that exception. What if you pulled it down here at 10 centimeters? Now, what I said before, you release it. If you release it, there's no way it's going to go more than 10. If you throw it, now you've given it an initial velocity here, so it will, if it can, compress more than that. And then it could go, but then it finds its new equilibrium, new maximum, and goes from there. But if you release it from rest, then you do. Now, if you throw it downward and make it go down and up, then however far it goes, that will be again how far it goes up and down. But if you release from rest, it will never exceed that plus or minus 10. Now, we've mentioned this is modeled by trig functions. What trig function would you say that was? And you could say either one of two of them. Sine or cosine, either one. And if this was your initial position down here, then I would say probably a negative cosine. Now, in your writing that trig function, would that 10 centimeters come in to play anywhere? That would would be your A, your amplitude, because that's the maximum it deviates from the equilibrium position. So there's the amplitude, okay? Now we'll talk about frequency and other things later. The frequency depends pretty much on the spring material, so we'll get to that. Okay, suppose that the 10 centimeters is the maximum distance the ball moves vertically upward or downward from equilibrium or at rest position. That would occur if you release it from rest, okay, at 10 centimeters. Suppose further that the time it takes for the ball to move from the maximum displacement above zero to its maximum displacement below zero and back again is t equal 4 seconds. What would that be called? From its max all the way down, back to its max again, what would you call that? That's its period, exactly, okay? The period would be, and then once you know the period, you can get the B, right? Because you know that period is 2 pi over B for a sine or a cosine. Okay, assuming the ideal conditions for perfect elasticity of the spring, no friction in the spring, no air resistance, the ball will continue to move up and down, uniform, regular motion forever. Not going to happen, but if you had those ideal conditions, it would be. Okay? Now, from this spring, you can conclude that the period, the time to complete one full cycle, like we already said, is 4 seconds. You already came up with that. The amplitude that we mentioned was 10 centimeters. The frequency, now we haven't talked about frequency before. What is frequency? Anyone know?
Number of cycles per second.
Okay. And while your period is the number of seconds per cycle, the frequency is the number of cycles per second. So guess what that is? The reciprocal of the period. Okay? The frequency in cycles per second is exactly the reciprocal of the period, and vice versa, the period is exactly the reciprocal of the frequency. Because this is seconds per cycle, because that's one complete cycle, and this is cycles per second, which is exactly the reciprocal. The motion of that nature can be described by a sine or a cosine function, and is often called the simple harmonic motion. Okay? Pushing a kid on a swing, simple harmonic motion. Okay? There's just all sorts of examples all over nature. Kids playing on a seesaw, simple harmonic motion. Okay? Just all over the place. All right, so here's the definition, as if we hadn't said it enough. A point that moves on a coordinate line is in simple harmonic motion when the distance d from the origin at any time t is given either by d is equal to a sine, whoa, what in the world is that? Sort of looks like a weird looking W, it's not. It's the lowercase omega, okay? Capital omega is sort of like a horseshoe, lowercase omega is sort of like a W. So omega t, and what does that stand for? What do we call it in earlier renditions of this? That was our B, right? And what was the B? It was 2 pi over the period. The period is 2 pi over B. So this is 2 pi over, the period is 2 pi over omega, because that acts just like the B did before. So it's either D is equal to A sine omega t or D is equal to A cosine omega t. We have a special name for that omega now. Before we just called it B. Where A and omega are real numbers, and omega is always positive, never zero and never negative. The motion has amplitude absolute A, just like we had before, and the period is 2 pi over omega, just like it was 2 pi over B before. But now the frequency is, because here's the period, 2 pi over omega, the frequency is omega over 2 pi, which lends itself to the name. What we call omega is the angular frequency. The frequency is in cycles per second. The angular frequency is in radians per second, or angles per second. Okay? So it's called the angular frequency. Omega. The book doesn't really talk about it yet, but that's what it will be called. All right? So it says here, write an equation. This is example 6, which is on page 332, top of the page. Write an equation for the simple harmonic motion of the ball described in this figure, where the period is 4 seconds, and it says what is the frequency of that harmonic motion. Okay? Now, they don't say how you're beginning. Just because they draw this first, let's assume that we're starting on the equilibrium position. That should give you a hint of what trig function I'm going to suggest. What would you suggest? This is really where you're starting. Sine, exactly. But if this is really where you're going next, then this would not be a regular sine, this would be a... How will this differ? If that's where it goes from here down here, then this would be a negative sine. Exactly, because it's starting and going southward. Now, let me just give you a hint here. The only way it gets from here initially to there as its next stop is going to be if you give it a velocity. So you have it here and you thump it, or you throw it, or you do something to make it go down. Then you'll go down to the minus 10 centimeters. Okay? So we've got our general form. It's going to be a minus sine. You could have done a cosine. It's okay too. Okay? What else would you be? What would be the equation? And let me just write down again what the recommended equations are. It's D is equal to A sine or cosine omega t. Okay? Now, so it says write the equation. What you have to figure out, you can leave D alone. In fact, you could call it y if you wanted to. So it looks more like a variable. So y is equal to, we need to come up with a value for A, and we need to come up with a value for omega. Okay? Now, anyone make a guess on the A? 10. Okay, that would be 10 centimeters. So this would be 10, I'll even write in centimeters, times the sine. Now, before we go any further, let's back up to what they tell us the rest of it. The period is 4 seconds. Okay? Now, if you know that, the period is 4 seconds, or it's right here, period is 4 seconds. Okay? What do we know about the period? I think, is that not? Okay, the period is equal to 2 pi over omega, since that's what we're using here. Okay, so what would that make our omega to be? Jalen's here. Now, will any of you see Walter, Gavin, or Chris, the 3 people we're still missing? Any of you typically see them? Not? Okay. Since Jalen just came in, let me go over something, because I don't know if you were here last time to hear it. Next Tuesday, I have a doctor's appointment. It's at 10:40, okay? But I have to be there at 9:40 for labs, so therefore it wipes out this entire class, okay? I was like, yes.
Did you pass out the test?
Yeah.
You
Pardon me?
got extra test?
Yeah, I'll give it to you then. I was in the middle of the announcement, okay? So, because between the labs, the appointment, and the time it'll take me to get back, we are not going to meet on Tuesday. There is no class on Tuesday. And the class decided, they demanded that we make up this class Friday at 9 o'clock, okay? So I'll be here Friday at 9, and we'll do 9 until 10:15. 9 until 10:15. Now, if you can't make it, it'll be recorded so you can catch everything then. Now, not tomorrow Friday, next Friday, okay? So we'll talk about it next Thursday as well. If you can't make it, don't sweat it. It'll all be on YouTube, okay? So I hated for you to lose a class, okay? So, no class on Tuesday. We will have class on Thursday, and we will have class next Friday to make up the Tuesday missing, okay? Now, the other thing is right after today's class, I've got to go to the Birmingham campus and pick up a vehicle because I've got to take my next class on a field trip. So I've got to get over there and get the vehicle back here before the next class. So, just to let you know, my office hours have changed some today. Okay, now you wanted the test. Let's see, did everybody else here get the test? You did not? Okay. Get it for you too. Okay, and I'll say there is quite a bit of graphing to do on this test. Would you take one to her too? So do you need graph paper? Jayla, before you go, do you need graph paper?
Yeah, graph paper.
Yeah, you got graphing to do. Do you need graph paper? Okay. Do you need graph paper too? Okay. So let me find it. It's in here somewhere. Okay, there are 9 to graph. Okay. Okay. There's 9 to graph. Now, the rest of you either said you didn't need any or whatever. But if you could get 2 on the front, 2 on the back, 4, 8, if you could get 3 on one of those, well, 2 pieces of graph paper front and back. What's the best one? Huh? That's the best one. Well, that's all right. I mean, this is pretty lousy quality, just because the copier in the copy room went down. It's been down for probably close to 2 weeks now. And so she had to use the backup copier, which the reason it's a backup is it doesn't print dark enough. Okay? So if anyone else needs graph paper, I've got some if you need it. So try to get 2 on front, 2 on back, 2 on front, 2 on back, and somewhere do a third one on one of those faces. Okay? Now you using your own graph paper, you can do it however you want to. Okay? You can do all 9 on one side, 5 and 4, 1 per page, front and back, whatever. Okay. All right. So now we got that period is equal to 2 pi over omega. So what would that make omega? Okay. Omega would then be pi over 2. Because we know the period is 4, so omega would be 2 pi over 4, which is pi halves. So then omega is pi halves times t. There it is. There's our equation for this. Oops, one thing I left off. What was that? The minus sign, because it's going down first, not up first. Okay, so it'd be minus 10 centimeters times sine of 2 pi t, pi over 2 t. Does that make sense? See how you work it? Any questions? Okay. All the stuff we've done before still contributes here. Any questions? Okay. Oh, and Jalen, one other thing I just recalled that I probably need to say before. This week is the last week of the first mini-term. Are you taking a first mini-term course? Okay. So that means next week starts second mini-term. And that means one thing it means for this class, my office hours on Tuesday, Thursdays, not on Tuesday because it'll be starting later, but office hours from now on Tuesday, Thursday will be 11:15 at the end of this class till 3:15 because my second mini-term class, because automotive students are in it, physical science class, they won't be starting until 3:15. So that means I have 2 more hours of office hours than I normally do on Tuesday, Thursday. That'll be for the rest of the term. And that means I'm here till 7:45 at night, Tuesday and Thursday, which is a lot of fun. Okay. Now, let's see, no. Oh, the other thing about being midterm, they usually ask for midterm progress reports at midterm, okay, which is now, next week. And in that, I have to report anyone who has a D or an F at midterm. They don't care about A, B's, and C's, only D's or F's. And that means that I need a score from you or else I've got to report. So if you haven't turned in either a paper or the first test, if you could get it to me over the weekend, sometime Monday or Tuesday, that way I can get it graded and have a score in the book for you for midterm. Okay? Otherwise, I have to report that you are failing at midterm, which I don't want to do because I don't think any of you technically are even anywhere close to failing, but we'll see. Okay, there's our equation. Write an equation for simple harmonic motion of that. Any questions about that? Oh, we didn't answer the last question. What is the frequency of that harmonic motion? Anyone tell me what frequency is? Really easy. 1/4. And what are the units for frequency? Per seconds. Okay, 1/2. There is another unit that they use for frequency. Anyone know what it is? We usually say cycles per second. Cycles really isn't anything you measure, so it's just the unit is per second. Anyone know the other unit? Named after Heinrich Hertz. 1/4 of a hertz. Okay, on your radio dial you have AM in kilohertz and FM in megahertz. Usually your TV is in megahertz. That's what they're talking about. Kilo would be thousands of hertz. Mega would be millions of hertz. Okay, this is 1/4 of a hertz. Okay, or per second. All right, let's see how they did the problem. Because the spring is at equilibrium, D equals 0. When T is equal to 0, use the equation D is equal to A sine omega T. Okay? Moreover, because the maximum displacement from 0 is 10 and the period is 4, you have the following amplitude as absolute value of A, so that would be 10, and the period would be 2 pi over omega, which is 4. So omega would be pi halves, just like y'all determined. Okay? Now, consequently, an equation of motion is D is equal to 10 sine pi halves T. With everything correct except we did a minus 10 because it started going down according to the figure. Note that the choice of A is equal to 10 or A equal to negative 10 depends on whether the ball initially moves up or down. And the figure they showed us showed it going down first, so that's why I chose that. The frequency, now this is so bizarre they did it this way. They say the frequency is omega over 2 pi, which omega being pi halves over 2 pi would then be pi halves over 2 pi, which would then be 1/4 of a cycle per second. How bizarre. Why go back and use omega when you had the period already? Frequency is 1/period. You could do it in 1 step, not 2 steps. Much easier. Okay? And they don't give the proper units for it. Okay? There is a checkpoint at the end of that. Highly recommend you do the checkpoint. Okay? All right. Now, here is an illustration of the relationship between sine waves and harmonic motion. Is the wave motion that results when a stone is dropped into a calm pool of water. The waves move outward in roughly the shape of a sine or a cosine curve. This one, if this is your initial point, that seems to be a max. So what curve would you use to represent that? Starting at its max. Cosine, that would be the cosine. So roughly, if you just did a cross section here, Starts at its max, goes through its equilibrium somewhere there, down to its min, up to its max, down to its min, up to its max, down to its min, to its max. Now, sure enough, water will dissipate those peaks and valleys just because water has internal friction also. You don't think of water having friction. It does. If water didn't have friction, you would not be able to swim. Okay? You might float, but you wouldn't swim. You could push as much as you want to, kick as much as you want to. If there wasn't something resisting the kicking and the pushing, you sit right there. Okay? If you're a sinker, you're done for. Okay. Now, they also show this. An example, suppose you are fishing and your fishing bobber is attached so it does not move horizontally. As the waves move outward from the dropped stone, your fishing bobber will move up and down in simple harmonic motion, as shown here. Now, frankly, I can figure out what they're talking about, but it sure is a lousy illustration to me. If this is your initial motion, and then a few minutes later the wave is moved downward, then you would be here, so now your motion's there. A few seconds or something later, it's here, and you moved up to here, and then a little bit later, you moved up to there, and at some point, you're going to go back to your max and go down. So your bobber is just going like this, but that's still simple harmonic motion because of its displacement from the equilibrium. Again, to me, this is a pretty sorry illustration, but I see what it's talking about. All right, and that, I believe, is the last slide, okay, which is not the last example, okay? So let's back up and do the last example. Example 7. Consider the equation for simple harmonic motion. D, distance, you could call it y or whatever, is equal to 6 cosine 3/4 pi t. Find A. First thing it asks for is maximum displacement. Anyone take any more than a nanosecond to figure that out? 6. That's your amplitude, so that is the maximum displacement. Now, they don't have any units given here, so we'll just say 6, whatever that is, okay? That's pretty simple. Let's do the B part. That's what your amplitude is, maximum displacement. The B, the frequency. What would be the frequency? Get out of there. Now, you can take as many steps as you need to. Where would you begin to get the frequency? Help me. 3 pi over 4, exactly. Second? Frequency. Okay. What is your omega here? Okay, that is your omega. So your period is what you're telling me, is that right? Or are you going straight to frequency? Huh? Okay, that's what I'm getting at. Which were you giving me? Frequency or period?
I was giving you the frequency.
Okay.
Omega over 2 pi.
Okay, all right. That's the formula we just had, and I'll get back to answer your question in just a minute. So the frequency is F is equal to omega over 2 pi. Now, what I want you to notice, okay, everything's good. You got a car, I've got a car. Your car's, yeah, and your car's over here. Okay, and you'll go get it, what?
I'm going to get it now, so Leanne go to lunch at whatever time she plans on going to lunch.
Oh, is Leanne back?
She is back, yeah. I talked to Miss Cleveland. Miss Cleveland knew everything.
Right.
So LaShonda was off campus for a few hours.
Okay.
So Miss Cleveland, her partner or whatever.
I don't know her yet, okay.
She knew everything, though, so obviously LaShonda told her everything. So she said, call Leanne. I'm like, hey, I called Leanne's back. Leanne's back, though.
Okay,
That's
good.
good, whatever it was.
And Leanne knows about it too.
Yeah.
Okay. All right. Good deal.
All
All right. Well, then
right.
thank you so much.
You're welcome. Thank you.
All right.
Let's see it for the day.
Okay. Now, Dawson just told us the frequency was omega over 2 pi. Does that look at all familiar to anything else? Period. Exactly. Period is 2 pi over omega, or 2 pi over b, right? So frequency, you asked what frequency was, it's the reciprocal of the period. Because the period is how many seconds it takes to make one cycle, if you're dealing with time. And what frequency is how many cycles per second. So those are exactly reciprocals of each other. So this is the reciprocal of the period, which would be omega over 2 pi. And what is your omega in this problem? Help me. It's 3/4 pi over 2 pi. All right. Now, one thing I notice is the pi's can divide out. That's sort of nice. And that would leave you 3/4 divided by 2, which is the same as 3/8. Does everybody see that? 3/4 divided by 2 would be 3/8. Does someone need to see that done more mathematically? Is that all right? 3/4 divided by 2 is 3/8. Do it this way. 3/4 divided by 2 is 3/4 times 1 over 2, which is 3/8. Okay, so that's your frequency. That's the B part. The C part. The value of D, I said C and wrote D. There's something wrong somewhere. Okay. I'm sorry?
Frequency is the same thing as period.
No. Frequency is 1 over period. Period is 2 pi over omega. Frequency is omega over 2 pi. So what period would be, frequency is 1 over period. Okay. Think about it as a frequency is in cycles per second. CPS, sometimes called. Well, what is a period? It's how many seconds it takes to make a cycle. That's the period. So they're reciprocals of each other. So whereas this period is 2 pi over omega, frequency is omega over 2 pi. They're exactly the reciprocal.
I thought that's how period was working.
So period is 2 pi over omega. Period is 2 pi. We used to call it B, now we're calling it omega. I've got to go different stuff.
Yeah. See, he didn't give us the option of not coming at all. He just said,
Yeah, he's been talking about this fucking.
Did you get the message?
Can we just tell them as a collective that we didn't vote on it?
Huh?
He literally brought up every day. Makes his class.
I've never had to make it. Me either. Like, I thought it was, you didn't come and like, yeah.
So you come?
I don't know. We might have a game, to be honest with you. I don't know.
It'll be so bad. He's
Friday?
teaching to
It's
himself.
gonna be about 2 people here.
Wow, he's gonna be in here teaching to himself.
Yeah, seriously.
Everybody's just like, I don't watch that video. Did you see it?
Who started the test? Have you started the test? You know it?
I agree.
Like, do you know what we've been doing now?
This section, I guess.
This
Last
section.
one.
I'm talking about all of like this new stuff. So I took the test and I was like,
I'm gonna look at it.
No, Number 4. Look at number 4. You made that shit up.
Yeah, what the hell? Whoa, shit. Let me go to my notes. That shit. Oh, that shit crazy. Yeah. You got my, all right, you got it out? I'll tell you my number right now.
Now look at number 9. I'm surprised you said that you don't understand because you be the one with the book and then you.
Well, it's easy just to look at the book and answer his questions. You don't have a book.
These examples, not these questions.
All right, 662, no 205. 662, 316, 6788. Did you send the front? Hello? No, I didn't. I can't be added. It says I've been added.
Add me. 205.
He was so serious.
675. 6232.
Sorry about that. Students in my last class were supposed to bring their papers down here, and they left them on the podium, and I didn't want another class coming in, and so I'm losing the papers. So sorry, I should have turned off that. Okay, did y'all get it straight?
Yes.
Okay, all right. All right, so that was the B part. Let's see if I can write C this time. Yes, I got it done this time. The C part says, C part says the value of D when T is equal to 4. So we're looking for D when T is equal to 4. Okay? Here's your equation. Okay? Can you tell it to me? No, we already did that. Okay? It said, what is the value for D when T is equal to 4? There's your equation. So you, like Glade, plug it in. 6 times the cosine of 3/4 pi times, and instead of T, we put 4. Okay? And what would that give you? No? Well, let's see. Okay. 6 times the cosine of 3 pi. And what is the cosine of 3 pi? -1. So therefore this would be, if cosine of 3 pi is -1, then this will be -6. Okay? There is the C part, right? And then the D part. Okay? Yuck. Running out of room. So what I'm going to do is erase some of this stuff over here. That was sort of just scratch work anyway. Okay? And the D part says the least positive value of T for which D is equal to 0. Smallest T for which D is equal to 0. Okay? Now remember, we take T positive only. Time is only positive. Okay? So what's the smallest value for T for which D would be 0? So here's your equation. What's the first place that cosine becomes 0? What would be the argument for it?
When it's on the x-axis.
Yeah, on the x-axis, when it crosses the x-axis. What would be the first value in here that would make this equal 0? Where is cosine equals 0 first time? It starts at its max amplitude.
So, what is this, altitude?
Pi over 2. So this thing right here would have to be pi over 2. So we'll do that to be 3 pi over 4t would need to be pi halves. That would make the cosine 0. So solve for t. How would we do that? Solve for the t. You can answer it one of two ways. Okay. Okay, that's one way is dividing, but because it's a fractional form, I prefer to multiply by 4 over 3 pi. Isn't that the same as dividing by 3/4 pi? Okay, so let's multiply this side by 4 over 3 pi. Multiplied by the reciprocal is the same as dividing. So both of these go out. So now we have t is equal to, and what are we left with here? Two-thirds, and we'll assume that's in seconds. We don't know for sure, but I'm going to assume 2/3 of a second. That's the first time. They don't have a unit either, so they just say 2/3. Okay. It could be a minute. It could be a year. I don't know. There is a checkpoint there, well worth your effort to try to do the checkpoint. And there's a little summary exercise there. And then we have our vocabulary. Let's do the vocabulary for 4.8. First one. A blank measures the acute angle that a path or line of sight makes with a fixed north-south line. The acute angle it makes with a fixed north-south line. It's not a ball. Bearing. Okay, very good. Okay, number 2. A point that moves on a coordinate line is in simple blank blank when the distance d from the origin at time t is given by either d is equal to a sine omega t or d is equal to a cosine omega t. Simple blank blank. Harmonic motion. Very good. Number 3. The time for one complete cycle of a point in simple harmonic motion is its blank. Period. And the number of cycles per second of a point in simple harmonic motion is its frequency. Got it. Homework exercises, and do any of the odds 5 through 11. They're all at Calc Chat. 9 is at Calc View. Do either 13 or 15. They're both at Calc Chat. 15's at Calc View. Do any of the odds 17 through, goodness gracious, 43, okay? There's quite a few to choose from. I would do more than just 1 or 2, maybe. Do any of those odds, 17 to 43. They should all be at calcchat.com. Then, simple harmonic motion, do either 45 or 47. They're both at CalcChat. And some more application problems. Number 49 should be at CalcChat. Then simple harmonic motion, either 51 or 53. They're both at CalcChat. And then 55 or 57. They're both at CalcChat. There's a true-false, 59. And that should be at CalcChat as well. Okay? Now, if you need a little bit of review, the chapter summary is great. It does it by sections, 4.1, 2, and 3, and 4. They were all covered in the first test. For sections 4.5, 6, 7, and 8 are all covered in the second test everybody has now. If you need a few more practice problems, the 4.1, 2, 3, and 4 were all for the first test, but if you need some of those, any of those odds will work. Now here's the thing about the review problems. Their answers for all of them are in the back of the book, but at calcchat.com only the odd numbers still are there. But for this test, if you need some to go back and check on, you could do any of the odds 63 through 67. They're all at CalcChat. 69 is a CalcChat. In 4.6, 71 or 73, they're both a CalcChat. And 75 is a CalcChat. Either 77 or 79, they're a CalcChat, either 81 or 80. Oh, these are in 4.7. 81 or 83, they're both a CalcChat. 85 is a CalcChat. And either 87 or 89 is a CalcChat. 91 is a CalcChat. Excuse me. Okay, 4.8, any of the odds, either 93 or 95. They're both a CalcChat. There is an exploration, true-false, 97. It should be at CalcChat. Okay. And then 101, if you want to look at that. I doubt if that's a CalcChat, but you can if you want to. Then another really good thing to look at would be the chapter test. Okay? The answers in the back of the book are for all of these, but for CalcChat, it's only the odds. And the ones that this one would be covering would be 11 through the end. So 11 or 13 would be at CalcChat, 15 would be at CalcChat, and any of the odds, 17, either 17 or 19 would be at CalcChat. All right, there's proofs in mathematics. One of the many proofs of the Pythagorean theorem is given. There's a problem-solving exercise that if you want to take a look at that, you can too. All right, any questions on chapter 4? You had the first test on the first 4 sections. You just now, everybody's got the second test. Please get back to me either your research paper or your first test. If you haven't already gotten it back to me, one of those back to me, so I have a grade for next week. All right. Then, if there's no more questions, let's move on to chapter 5. All right. Okay. We'll do 5.1. Now, the title of chapter 5, as you'll see come up in just a few minutes, right there it is analytic trigonometry. What do you think of when you think analytic? Analyzing something, and in mathematics that usually means solving, say, equations, finding you're dealing with sort of abstractions, generally. Though there are practical problems to it, as you see, each of these illustrates a somewhat practical problem. Okay? So, even though we had them back in the first part of chapter 4, your fundamental identities, chapter 5 is going to be using these to do analysis, analyzing, okay? Using the fundamental identities. So you're going to see them again and again and again. So let's go. We'll first recognize and write the fundamental trigonometric identities, and you know every one of them. We've already dealt with them. And we'll use these fundamental trigonometric identities to evaluate trigonometric functions, simplify trigonometric expressions, and rewrite trigonometric expressions. So that's what this section is all about. Introduction. Okay. We'll learn how to use the following, use the fundamental identities to do the following. What we just said. Evaluate trigonometric functions, simplify trigonometric expressions, develop additional trigonometric identities. Okay? So we've got some, we will be looking for some others. And then we'll solve some trigonometric equations. Now, yeah, we do all this, but most of this chapter is going to deal with trigonometric identities. Not all, but most. Okay? Here are those fundamental identities, and you know them all. The first group here are called the reciprocal identities, and we've used them time and time again, so it's pretty straightforward. Sine is 1 over cosecant, and therefore cosecant is 1 over sine. Cosine is 1 over secant, so therefore secant is 1 over cosine. And tangent is 1 over cotangent, and cotangent is 1 over tangent. Those are your reciprocal identities. We'll use those a lot. Now, frankly, I never go this way. If I have a cosecant, I'm going to change it to sine. I very seldom will change the sine to a cosecant. Those are just harder to deal with. Okay? I'll quite often, if I'm given a secant, put 1 over secant and give me a cosine. Very seldom will I ever go from cosine to secant, though you can. And most of the time, I'll take a cotangent and make it into a tangent rather than making a tangent into a cotangent. Now, those are your reciprocal identities. They're all true. They're all always true. By the way, they haven't done this yet. They're going to do it later. When you see an equal sign, what you usually think is that's a part of an equation. And these are in many ways equations, but the difference between this and 3x plus 7 is equal to 4, okay? That's an equation, but that's true for only one value of x. Other equations may be true for only selected values, okay? What these are true for every value. For every value u, except where you can't do it, okay, these are true. So that's the difference. These are called identities rather than equations. They are a type of equation. That's what makes them identity. This is always true too. That the tangent u is the quotient, or I like to call these other texts, call them the ratio identities, the ratio of the sine to the cosine. We've done this repeatedly. Cotangent is the ratio of cosine to sine, or the quotient of cosine divided by sine. Now, of course, these are true anytime cosine is not 0, sine is not 0, and basically that's true for all of those. If you have a denominator, of course that denominator can't be 0. Okay? Now, a third one, and we've done these several times before, your Pythagorean identities. They come basically from the Pythagorean theorem. A squared plus b squared is equal to c squared. On a unit circle, c squared is 1. So the sine squared, which is the y squared, plus the cosine squared, which is the x squared, on the unit circle is always equal to 1. But this is true for any. You don't have to be on a unit circle. Sine squared plus cosine squared is always 1. That's what makes it an identity. There aren't any restrictions there. Okay? Now, you remember how to get from here to here? This one to that one? Basically, divide everything by cosine squared. Cosine squared over cosine squared is 1. Sine squared over cosine squared is tangent squared. And 1 divided by cosine squared is secant squared. Okay, so that's how you get that. The other one, divide everything by sine squared. You get 1 plus cotangent squared is equal to cosecant squared. Okay. Now, those are your simple, straightforward. Goodness gracious, we can't be out of time already, are we? Yeah. Okay. Okay. We didn't get enough done here to give any new homework exercises, I don't think. Let me check and see. I don't think so, but let's see. Now we'll pick up those later. So we'll pick up next time at, let me make a mark here, at the Pythagorean identities. We already hit the first part, but I want to mention a couple more applications of the Pythagorean identities. Okay? And then we'll move on from there. All right. Any questions? What is next time? Thursday, not Tuesday. Okay? All right. Good deal. Thank you. Excellent.